This session is going to cover some of the starting material on Module 3, which is all about derivatives. And the basis of derivatives flows all the way back to all the time, trying to find the slope of a curve at a point. So let's kind of back up and talk about what we already know about slopes of lines, because we did slopes of lines way back in grade 10. So if we were asked to talk about a line, say I gave you something like y equals 2x plus 1, and you don't have to really remember how to graph it, but you graph the y-intercept of 1, and you go up 2 and over 1, and you get this nice line. The slope of that line is always 2. Anywhere along there, if we talk about where I've got a green highlighter, it's 2, and where I've got kind of the light blue, and then if I do like a red, all of those slopes are 2. The slope of a line is always constant. So that's something we learned way back when. Might be very interesting and good for you to note that you will have to use the slope formula for some of the introductory questions in the module. So there's the slope formula, which you'll see us will do a few questions surrounding the slope. What happens though if we look at a curve? Now, a curve that we spent a lot of time in grade 11 looking at was the quadratic function y equals x squared. So if we look at drawing that, and again, just trying to get a bit of a sketch, my diagrams are not perfect, it looks like that. And so then what if I said, ponder, question, what is the slope of the curve? Just say that's just the question I threw out. Well, let's think about it. If we do the same thing with color, what's the slope of the curve there versus what's the slope of the curve down here versus the slope of the curve here? You can see that those would be very different slopes. At the red, it's kind of increasing quite quickly. The green point that I chose, it would be 0, it was not going anywhere. And at the yellow, it would be increasing negatively. So the slope of a curve changes. How is that going to lead in and help us with anything? Or let's talk about how we would find the slope of a curve. Okay, so that's kind of where we're leading. So how do we find the slope of a curve at a point? So the process that we show here is we talk about, and again, I'm just going to take the nice, easy example of y equals x squared, because we don't want the math to get super hard. We want just the idea to kind of be fleshed out for us. So if we look at this curve and say I want to find the slope of the curve at the point 1, 1. What we can do is we can start by getting a sense of how to find the slope of a curve by finding slopes of secant lines. Okay. Now, you might not know what a secant line is yet. Secant line, and not really trigonometry. I know that that's a word in trigonometry, but it's not trigonometry based. The slope of a secant line is a line that cuts a curve twice. Okay, so if we take this point right here, 1, 1, and let's say I'm going to draw a secant line between 1, 1 and 2, 4. So we'll see how good my drawing is here. We could find the slope of that secant line, and why don't we just call that line 1? So line 1, the slope of that would be y2 minus y1 over x2 minus x1. Throw the points in, we go 4 minus 1 over 2 minus 1, we get 3 over 1. So the slope of that line would be 3. Now, is that representative of the slope of the curve at 1? Well, not really, because it crosses out 1, 1, and then goes way up and crosses at 2, 4. So the idea that we're looking at here to start getting us the idea of derivatives is we're going to take that secant line, which, you know, if you kind of look at my fingers, is about that long. And we're going to make it shorter and shorter and shorter and shorter until it's a tangent line. A tangent line is something that just basically skims across the curve at a point and just kind of touches at one point. Okay, so let's say that we want to make a shorter secant line. We're not going to do this a lot, but I need to get the idea across. So let's say we take a point like right in the middle here. So the point would say be 1.5, and then 1.25 squared is 2.25. And I'll change the color of my pen, and we'll be looking at, we'll call that line 2. So when we go and look at the slope of line 2, again, probably don't have to continue to put the slope formula down, but nonetheless, 2.25, take away 1 over 1.5, take away 1. We get 1.25 over 0.5. I don't have that number. I guess that would be what, 2.5. But we'll just double check here in our calculator. So 2.5. So the slope now of that is 2.5. And that is a shorter secant line. So the idea of what I just explained it, but I'll explain it again. We're trying to make the secant line shorter and shorter and shorter and shorter until it's a tangent line. So I'm just going to write that down. If we can make the secant line shorter and shorter, it becomes a tangent line. Now again, if this is your first exposure to this, a tangent line is a line that cuts a graph once. So if we can do that. Now, the math behind this, let's talk about that, because I kind of really want to get into derivatives, but I want to give you some of the background here. If we looked at 2 points on the secant line, say point 1 being, we're going to look at this nice curve, again, the easier one, and we're going to talk about point 1, 1. And then we're going to look at a point that's a little tiny further down the line, 1 plus h. And what that means is just a little further along than that. And then the y coordinate of that would be 1 plus h all squared. That would be a second point. Again, this h value is, in our case up here, in this one, the h value, let's see, I'm just circling. The h value here would be 1, because we went from 1 to 2. The h value here would be 0.5. We went from 1 to 0.5. It's getting smaller and smaller and smaller. Now, you might remember limits from module 2. So if we wanted to find the slope of the tangent line, we can find the slope of the secant line and then do the limit as h goes to 0, which means that h would be coming closer and closer to 1, and that would give us our slope. So let's have a look at, we're not going to do this calculation a lot, but again, our slope formula is y2 minus y1 over x2 minus x1. So we put our y2 value of 1 plus h squared, take away 1 over 1 plus h, take away 1. Now, let me do some highlighting in case you're getting a little confused. This is our y2. There's our y2. This is our y1. There's our y1. This is our x2. So I'm doing this color green. This is our x1. So to find the slope of the tangent line, then we're going to say we want to find the limit as h goes to 0 of this function. So we have to do a little bit of math here. 1 plus h squared. Let's take that over here and remind you that we have to do FOIL. So 1 plus h times 1 plus h is 1 plus 2h plus h squared minus 1 all over 1 plus h take away 1. We'll simplify that bottom. And we just do a little bit of simplifying here. So The ones on top are going to cancel. The ones on the bottom are going to cancel. And we're going to get the limit as h goes to 0 of 2h plus h squared all over h. Okay, you see a little bit of factoring maybe. Again, this is we're finding the slope of the tangent line. So last step here, we factor an h out and we get 2 plus h all over h. Now we can cancel those. And now we can apply the limit as h goes to 0. We're putting a 0 in there and we get 2. What this tells us is the slope, oops, sorry, not the sloped, the slope of the curve y equals x squared at the point 1, 1 is 2. The slope of the tangent line tells us the slope of the curve. That is the whole basis for what we're trying to look at when we talk about doing derivatives. So I want to jump into talking about how we do this in a little bit different manner. There are a number of different rules. If you have your formula sheet handy, you might want to pause this recording and grab your formula sheet out. Because what we do really is we look at this idea of the longer version of taking secant lines, making them into tangent lines, and then we say, oh, is there a little bit easier way of going about and doing this? Okay. And so I'm going to show you that little bit of easier way, jumping into the rules. The first one that we look at, and I'm going to use this that I just did here, I'll circle in orange. I'm going to use kind of as a basis for a bit of my conversation today. So we keep on referring back and hopefully you can tie things together. So we're going to talk about the power rule. So I don't know that we would every time want to find a secant line, make it shorter and shorter and shorter, find the tangent line by doing the limit as it goes to 0. That idea is called first principles, what we just did here. And you will have to do that some of the time, but we really don't want to always do it all of the time, okay? So when we look at a bit of a different way to do it, we look at a power rule. And some of you might already know this. Again, I'm just going to go back to y is equal to x squared. And before I introduce the power rule, I need to talk about some of the symbols that we use when we are trying to show derivatives. There are 3 ways of showing derivatives. Y with a little dash, we read that y prime. We can go dy dx. Now what that says is take the derivative of y with respect to x. This is kind of the better way of doing it, but I find it, if I can do y prime, it's a little bit easier. And then another way of saying the derivative is dx of y, which is the same thing. The derivative of y with respect to x. Both of those are kind of read the same way. So what is it that I'm talking about when I talk about the power rule? Well, I'm going to give you this answer and then I'm going to pause for a minute and then I'm going to let you see if you can figure out what we're doing to do this. So the derivative of y equals x squared is 2x. You see, I don't know. I mean, maybe that's not enough information to show you. Let's give you another example. If I say y is equal to x cubed, and then I ask you for the derivative, that's the derivative. You see a pattern emerging. You might see, and you might have already looked at this, and this you might be watching this recording as a bit of a help review. The 2, the exponent drops down in front, and then we subtract 1 from that exponent. So that's where the 2 comes from. Then we add 2 take away 1, which gives us 2x to the first, or just 2x. So the whole idea is we take the exponent, we drop it down in front, and we subtract 1. Now I'm just going to pull up the actual way they write the power rule on your formula sheet. Okay, so I'll write it in a nice green. So this is how they have it on your formula sheet. That it says d, the derivative of some sort of function ax to the n is n times ax to the n minus 1. Again, let's just unpack that a little bit. A is just a coefficient. I didn't have a coefficient in my questions initially. And then you can see that the n comes down in front and then the exponent gets subtracted by 1. That is kind of the base rule. We're going to play around with that and work on doing different power rule questions. So let's practice a little bit of power rule before we go on and talk about some of the other algebraic rules, because now I'm going to kind of pivot. I'm going to talk about the algebra side and doing some of the tougher questions algebra wise. So let's just throw another question at you. Find the derivative of, let's say, y equals 3x squared plus 2 times the root of x. Let's say, let's try to put something funky in there, plus 5. Okay, again, you might want to pause the recording, think about it, write it down, and then start it again. So the idea is we're going to drop the exponent down and subtract 1. Now, I don't like how this is written particularly, so I'm going to stop and I'm going to put the x as a half power and then just plus 5. Now I'm going to be ready to rock and roll. So I'm going to use dy dx this time. Do be careful. Something I want to note. Make sure you write something on the left-hand side so I know whether you're talking about the function or the derivative. Because as we go through this, we're going to be finding first derivatives, second derivatives, etc. You need to tell us what the expression is or we get lost in it. So we have 3, we bring the 2 down, and then we get x to the first power. Then the next one, we have 2, we drop the half down, we get x to the minus half power. Now, 5 gives us a little bit of a conundrum. Some people think the derivative of 5 is 5, but really what's hidden here is x to the 0 power, right? There's no x there, so we could put x to the 0 power if we wanted to. And so then we get the derivative of a number is 0. So the derivative of a constant is 0, okay? So then we could simplify this. Dy dx is 6x. The 2.5 cancel, so plus x to the minus a half power. I most of the time prefer to leave everything along one line. There's nothing wrong though with expressing it as this 1 over root of x. X to the minus half power would be 1 over the root of x. And that's okay as well. So that's a bit of a tougher question using the power rule to find the derivative. Now remember, what we're trying to find is this is an expression for the slope of this starting curve. So then I could give you an x coordinate. You could go and find the y coordinate and throw it, actually you just would have to find the x coordinate, throw it in there and you could find the slope of the curve at that point. So this is an expression that helps us to find the slope of the curve. I think we should move on and try to look at, and I'm trying to kind of be all things in this particular recording, trying to go through and do some of the harder questions. Let's talk about the next one that would come up. And I think before I talk about it, I'll give you another question and get you to ponder what's different about it. So find the derivative of, same exact lead in, but let's do something like this and see if you can see what I might be throwing at you that would be a little bit problematic, say. So let's say I gave us 2x minus 1 squared. Let's say that's what we had. And so if we were working on that, and we did the derivative of it, I'll just do y is 1 and we'd have to the first power. But we have a problem here that I've put us in. We have an expression in the bracket. When we have an expression in the bracket and we're trying to do these derivatives, we also have to do the derivative of the inside piece. So the chain rule arises when you have an expression inside with an exponent outside that also has a derivative. So really the idea of the chain rule, this is the next one we're going to do, and how you know whether in the world it's going to pop up on you is if you have an expression inside with an exponent outside, you got to watch for the chain rule. And the chain rule, basically what you do is you do the power rule. So you do the outside derivative. Then you do the derivative of the inside. Might be much vague for you to know what's going on, but that's okay. We're going to cover it. Again, I'm going to take a moment here to get the chain rule off of your formula sheet and throw it up here. So the chain rule, the way that it's written on your formula sheet, is this: dy dx is equal to dy du times by du dx. And as we go through doing derivatives, we'll flush that out a little bit more. But generally, it's finding the derivative of the entire thing multiplied by the derivative of the inside. So I haven't quite finished number 2 here. I did the derivative of the outside. So I took the 2 in the front, and then I subtracted the 1. So that part's done. Now I have to take the derivative of the inside. So we multiply by a further 2, because the derivative of 2x minus 1 is just 2. So our final answer here is 4 bracket 2x minus 1 to the first, or you can drop the exponents of the first and just write it as 4 times 2x minus 1. Note when you write these answers, they want the answers in fully factored form. If you're not sure exactly how factored, you can always reach out and ask, but we usually do want them fully factored. So let's do another practice one. Again, our lead in here is just find the derivative. Okay, so let's try one that, I don't know, maybe you'll find a little bit harder. Y equals, let's do the square root of 3x squared plus 2x. Okay, again, you might want to pause. So we have to do the derivative of the whole thing and then the derivative of the inside. So I'm going to get ready by changing it to a half power first. Like that. So notice I have not done any derivatives, so it's just y on the far side. And I'm just going to alter which terminology I use, because remember, they all mean the same thing. So dy dx is equal to the outside 1/2 times the inside not changed to the minus 1/2 multiplied by the derivative of the inside. So the derivative of this is 6x to the first plus 2. Put that in a bracket like that. Now that's kind of ugly. We can do a little bit of work on this to make it a bit nicer. Let's put a half here. I'm not going to do anything with this. It's just going to kind of sit there. I can take a 2 out of this though and make it 3x plus 1. That's kind of awesome because that 2 and this half would cancel. And so my final answer, doesn't matter which order really you put it in particularly. I kind of like the 3x plus 1 to go in front, but it totally does not matter. And there would be our final answer. And if you wanted, you could put the minus a half power underneath as the square root. Make sure you finish off by saying dy dx. So again, that's an expression for the slope of the curve at a point. If I gave you an x value, you could plug it in and get a number. Again, I'm trying to get through the algebra. So far, we've done the power rule and the chain rule. Now, what if, again, I asked you the derivative, find the derivative. So I'll write that again because it's now way out of sight. Find the derivative. Say I really ramp things up and I give you something, again, kind of entirely different. So let's go 2x plus 1 cubed times the square root of x minus 1. And let's do that one, okay? Notice something different again. Now we've got 2 separate expressions. Here in this one, we had one expression, the root of 3x squared plus 2x. So we had a really yucky expression inside of a square root, but really kind of all one expression. Now all of a sudden, we've got 2 expressions. So when you have 2 expressions and they're multiplied together, I don't have a time sign there, but we have to know to infer there's a time sign. We are going to do the product rule. And again, if you have your formula sheet handy, you'll see all these formulas. Now we decide that it's a power product rule because we're multiplying things together. Now I'm just checking your formula sheet again to try to write it down exactly as they have it. So on your formula sheet, it says d dx. Now if u times v, I don't really know why we use those silly letters because a u and a v look so similar, but that's okay. So it's equal to u times the derivative of v dv. Sorry, try to make that a little bit more easily. Derivative of v plus v times the derivative of u. What I'll try to do is make sure my u's have tails. There's a tail. Okay. So what does that say to us? It says that we basically have two expressions. We find the original individual derivatives, and then we take one term multiplied by the derivative of the other, and then the second term by the derivative of the first. So I like to lay it out this way. I like to go over to the side on my question, and I identify u as the first expression given. I identify v as the second expression given. You see, I'm going to put it to the half power rather than leaving it as square root. And then I find the derivative of u with respect to x. So in other words, the derivative of this. We take the 3 down, 2x plus 1, we subtract 1 squared. Check for the chain rule all the time. You have to multiply through by 2, the derivative of the inside. So we get 6 times 2x plus 1 squared. That's the derivative of the first term. The derivative of the second term, dv dx, is 1/2 x minus 1 to the minus 1/2. And then we check the derivative here. But since we just have a 1x, we don't have anything extra. So that would be the final derivative. Now when we go to find dy dx or y prime, doesn't matter which one you use, we kind of cross multiply, right? It says u times derivative of v, so this times this. So it's 2x plus 1 all cubed times the derivative of v, which is 1/2 times x minus 1 to the minus 1/2. That's our first term. And then the next term are these two multiplied together. So plus 6 times 2x plus 1 squared. Doesn't really matter what order you put them in. I'm going to put them in this order because then my 2x plus 1 terms are first. And then we multiply by x minus 1 to the half power. Okay, so we have two separate terms. There's your first term, and there's your second term. Again, u times the derivative of v and v times derivative of u. I wrote the derivative of u first just so that my similar terms were lined up. Now we've got the derivative expression, but that would not be an acceptable derivative expression. We need to common factor this derivative expression. We have to be a little bit careful about how we common factor it. We have to take out the largest power of each of the brackets. And if there are any fractions, we have to take out the fractions as well. So let's see if we can do that. You'll likely need to practice this a little bit. So this 1/2, whoops, I don't like that color. Let me get a better color. I was going to use yellow. So let's use yellow. So this half has to come out. The 2x plus 1 squared, because remember when you're finding common factors, you take the largest common exponent. So between 3 and 2, the largest common exponent is the 2. And then between the exponent of minus 1/2 and the exponent of 1/2, the exponent of minus 1/2 is the common one, the smaller one, right? No, you have to take the smaller one. So what I've got highlighted there is our common factor. You take any fractions have to come out front, and then you take the smallest exponent on the one bracket and the smallest exponent on the other. That's the common factor. So let's see how this goes. We are then taking out 1/2 x minus 1 to the minus 1/2 multiplied by 2x plus 1 squared. Now we might find once we take the minus 1/2 out that we have another bit of numerical factoring to do. We'll have to see. So remember what common factoring means? It means divide each term by that factor. So what you're thinking here, and I don't normally write this down, but to teach it, I'll show you. I'm dividing this by 1/2 x minus 1 to the minus 1/2 and 2x plus 1 squared. So quite nice. This cancels, this cancels, this cancels, this cancels, and this goes in here and just leaves an exponent of 1. So we open a new bracket, and all we have left for our first term is 2x plus 1 to the first power. I'll leave the first power there so you can kind of track that that's the first term. Now the next one, we're dividing by 1/2 x minus 1 to the minus 1/2 and 2x plus 1 squared. Okay, so we can see the 2x plus 1 squared cancels. 6 divided by 1/2, careful, 6 divided by 1/2 is like 6 times 2, we get plus 12. And then when we subtract these exponents, let me just circle them with green, 1/2, take away a negative 1/2. That's the math that you're doing in your head. 1/2, take away a negative 1/2. It's 1. Okay, so then we're going to get x minus 1 to the first power. That may be your biggest challenge when you do these questions. It's just watching the factoring. So everything out front is totally fine. You can leave it like that. We just have to kind of tidy things up in here. So even though it's kind of a pain, we got to rewrite everything out in front like this. And then open a bracket. We're going to get 2x plus 1 plus 12x minus 12. Close the bracket. And so our final answer, 1/2 x minus 1 to the minus 1/2, 2x plus 1 squared. And then what do we get? 14x minus 11. All right, there's the derivative with respect to x. Lots and lots of content, right? Lots of algebra. So you'll have to watch this practice, watch this practice. Now to come, because we'll do another recording to finish up, we haven't done the quotient rule yet. Oops, nice spelling. So we'll make sure that we do that the next time around in the next recording. I hope you find that helpful.